And we're rolling. Welcome, everybody. First video of the year for calculus. I feel like that needs a round of applause. For those of you watching along in second period tomorrow, because you'll have to be watching this tomorrow, it's going to be good stuff. We're just going to get to as much as we can in this period. Hopefully get as much as possible done in this period so that we could just have a couple more slides to do tomorrow for you guys in here in the classroom. A couple more slides for you to do tomorrow, and then we'll have the rest of the time we'll be able to work on your homework in class. Sound good? Sounds good. All right, let's get to it. First section, actually the whole first chapter in calculus is a lot of just review. Okay, we're not really going to be doing anything new just quite yet. It's a lot of the same types of things, the things that we need to kind of brush up on before we get into like what is calculus. But to answer that question, what is calculus? Calculus was invented basically to find when instantaneous things happen. Okay, like instantaneous rates of change, or instantaneous rates of change. That's really one of the big topics in Calc 1. And we're going to be talking about that a lot. So section 1.1, 4 ways to represent functions. But let's start basics. Why do we need functions in our everyday life? Now, you can write down anything you really want to write down up here. You do not need to write down all of this stuff. There's a lot of stuff that you do not need to write down. It's really just up to you. There are going to be definitions that I'll say, yeah, you should write this down. But a lot of the introductory stuff is probably not going to be as useful as some of the other things. Now, problems that we do together, yeah, you're going to want to write those down. But let's start by talking about why do we need functions? Well, the basic need for functions was just to come up with a way to talk about things that are happening in real life and maybe relate them to a more mathematical way so that we could predict what might happen in the future, right? That's why we come up with a function. That's why we come up with an equation. Think about any, like distance versus time graph. If it's a linear distance versus time graph, well, then you can predict when something might occur. Like how long does it take until we get to 50 feet away? Well, you could predict when that's going to happen if you have a function to model that situation. Okay, so that's really what the basics are about why we need functions, to model real life situations so that you can somehow predict what's going to happen in the future or predict what might happen later on. So for example, let's talk about these different types of functions. The area A of a circle depends on the radius of the radius r of the circle. The rule that connects R and A is given by the equation A is equal to pi r squared. We know area of a circle formula, right? With each positive number R, there is associated one value of A, and we say that A is a function of R. Every one value of R, I could plug in a different radius, and it'll give me a different value for my area, right? It's not like I could get two different area values out by plugging in one radius, right? I'm talking about a function there. Right? I'm talking about every one input is equivalent to one output. Doesn't matter what I choose as my radius. If I choose one distinct radius, I'm going to get one distinct area, right? Human population of the world, P, depends on the time. The table gives, the table was in the book. But this is a function. This is that function notation there where we have some function P, and we say, okay, looks like T is time in this situation. World population P of T, population at certain time T, right? That notation is telling us that, okay, the population at year 1950 is about, 2.56 billion? Is that billion? No, that's billion. That's billion, yeah. But for each value of time, there is a corresponding value of P. That is a function, right? That constitutes a function. Every one input for the time, I get one population value as the output. 1 to 1. One input, one output. Function. The cost C of mailing an envelope depends on its weight. Think about it. If I plug in a certain value of weight, if I know a package weighs a certain amount, it couldn't possibly be two different costs, right? That is a function. Same thing, graphically. We know vertical line test, it'll come up later. Even something like this is the vertical acceleration A of the ground as measured by a seismograph, things that measure earthquakes, during an earthquake as a function of the elapsed time. Okay, think about it. At one given time, there is only one distinct acceleration, right? It's not like at any given moment I could have two different accelerations. That doesn't make sense. That is a function. We're going to be talking a lot about functions in this course. Okay. So by definition, this is our definition of a function. It might be a good idea to write down. It's kind of like nostalgia. This might be the last time you write down the definition of a function. A function f is a rule that assigns each element x in a set D exactly one element called f of x in set E. They're saying first set is D, second set is E. If I take one element in my domain, it maps to exactly one element in my range, right, in my outputs. We usually use the letter f, but it doesn't mean that we always have to use the letter f. We're going to be talking about many different functions at the same time. So f, g, h, j, l, those are all very common letters we use for function. Okay. A function f is a rule that assigns to each element x in a set D exactly one element called f of x in set E. That means the input is x, the output would be f of x. You know, normally we say sometimes y, where y is equivalent to f of x, input x, output y, input x, output f of x, domain x, range y, f of x. All those different synonyms for those. You know, thinking about it in terms of, we talked about domain and range. I'm kind of getting ahead of myself, apparently. Remember, domain is the x values, range is the y values. I mean, that's something that we've been learning since Algebra 1, right? Domain is x values, range is y values. Domain is input, range is output. Okay? Remember, this notation means the value of the function f at the input x, value of f at x or f of x. We could also talk about it when we work with word problems as independent versus dependent variables. Independent variable is always going to be my x value, my inputs. Independent input, x value. Dependent variable is always going to be my y value, what I get out. Input independent variable is going to change. Dependent variable is caused to change by the independent variable. Okay. This diagram here, this mapping diagram there, that's a very common one for functions where I can take each element in my set D. No matter what point I pick in that space D, it's only going to map to one point that I pick in that space E, right? Whatever I choose as my input, that's the notation that I use. So if I pick X, this is f of X over here. If I pick A, that's f of A over there. What if one element in my domain maps to only one element of my range? I couldn't possibly do this as a function, right? Actually, make it a different point. No longer a function, right? Just by taking one element of my domain and mapping it to two different elements of my range, no longer a function. If I have one output has the possibility of having two different outputs, just one, no longer a function. You got to have one input to one output, right? Graphically here, you know, we have this notation. This is f of 1, f of 2, f of x here. Remember that you can actually calculate those values graphically by just picking out the y value. Like f of 1 would be whatever I could see along the y-axis. This is 1 comma f of 1, 2 comma f of 2, x comma f of x, right? The domain is the x values. The horizontal, the range is the y values, right? So let's practice a little bit. I mean, we've been doing, again, this since Algebra 1. The graph of function f is shown. Find the values of f of 1 and f of 5, and then we're going to talk about the domain and range of f. We're going to assume that these are going to stop here, and those are not arrows on the end. We're going to make these closed dots right here. Wish they would do that, but they don't do that. Okay, so what is the value of f of 1? What is the value of f of 1? What is f of 1 equivalent to?
3.
So f of 1, that's how I make my f's for functions. I don't know. One of my calc teachers did that along the way, and I picked that up. You say 3. So f of 1 is 3. The y value that corresponds with the x value of 1 is 3. F of 1 is 3. Good. And what is f of 5? What's f of 5? F of 5 is, I got to look at it here. 1, 2, 3, 4. 1, 2, 3, 4, 5. What can we estimate that to be? Negative 0.75. Negative 0.75. I like that. Negative 0.75. Good. Remember, if I ever ask you what is f of something when I have a graph, you just find the y value wherever that x value comes to pass. Okay, let's identify the domain and range. So that was part A. Part B. Let's identify domain and range. I like to use interval notation to do this. So what is my domain? What is my domain? How can I describe the horizontalness of this?
0 to 7.
0 to 10. 7, good. 1, 2, 3, 4, 5, 6, 7. So we've got 0 to 7 inclusive, right? Remember, I would use parentheses if the endpoints were not included, open circles, but because these are closed dots on the end, we assume that those endpoints are included, 0 to 7. That's my domain. And let's talk about my range. What's my range in this case?
4 to -2.
4 to -2, but we would say -2 to 4, right? So -2 to 4. Just got to double check that. So down to 2, up to 4. Yep, good. Remember, left to right is your domain. Bottom to top is your range. Good, yeah. It's like Algebra 1, right? I teach that to my Algebra 1 students. Sketch the graph and find the domain and range of each function. Sketch, keyword there, sketch the graph. First thing we got is f of x is equal to 2x minus 1. We got g of x is equal to x squared. Let's do f of x first. Let me pull over a graph real quick. Oh, really? I got to save all those again? Oh, boy. Where's my content? No, get out of here. Oh, well. It's not there. 0 items. One time I drew a perfect circle on the board. And I had to save it. But now it's gone. Oh, well.
I don't believe you.
Draw it again.
Let's try. Here we go. No, that's awful. Oh. No, see?
Too quick.
So frustrating. So we got f of x is equal to 2x minus 1. You know, there's a couple different ways that we could graph these things. I'm going to have to do a little Bush League graph here. I would, this is a linear function. We can identify it as a linear function because of its characteristics, just an x value. And we can recognize that from our previous knowledge, that's y equals mx plus b form, right? Slope-intercept form. With a y-intercept of -1 and a slope of 2. So let's graph it that way. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Again, it's a sketch. I wish I could pull over a real graph, but So the y-intercept is -1 and the slope is 2. Y-intercept is -1 and the slope is 2. Rise 2, run 1, right? Rise 2, run 1. Rise 2, run 1. And it's a positive sloping line going up and to the right. Down to left 1. Kind of missed my point there, but you get the idea. Again, it's a sketch. Going up and to the right, slope of 2. Another way that we could have graphed that is just to pick some inputs, right? Do I need all of those outputs? Do I need all of those points? No, it's a straight line. I only need 2. But I only know that because it's a linear function, because I can recognize that it's a linear function. We're going to get to functions where we have no idea what it's going to look like. So we have to use not only our previous knowledge from Algebra 1, Algebra 2, Calc, but also our knowledge in calculus and say, what are the important points that I do need to pick so that I can get a clear picture of what's going on? I can recognize in part B here that I know that's quadratic. I know it's the parent quadratic, one that hasn't been transformed at all. I know because the x squared that it's quadratic, and I know that, hold on. Can't make a graph and talk at the same time. I know because there's nothing around it that it's its parent. I know because it's positive, it's a positive x squared, it's opening upward. I know that it has a y-intercept at 0 because nothing's being added or subtracted to it. I know because there's no parentheses on the inside being added, subtracting. It's not moving any left or right, not moving any up or down. No transformations has happened to it. But I could also say, if I had some inputs like 0, if I plug in 0 squared, I get 0. I plug in 1 squared, I get 1. I plug in 2 squared, I get 4. And I know it's reflected because it is a quadratic. Ooh, look at my scale is really whacked out there. But you get the idea. Okay. Just a sketch, people, just a sketch. But I've got my parent quadratic function. What I'm getting at here is that we know a lot about functions. We've studied a lot of functions, many different types of functions. Trigonometric, logarithmic, whatever it may be, exponential. we've studied a lot of different functions, and we have a lot of prior knowledge. There's a lot of different ways to graph a function. A lot of different ways we talk about functions as well. All right, let's take a look here. If f of x is equal to 2x squared minus 5x plus 1 and h is non-zero, evaluate f of a plus h minus f of a all over h. This is actually a really important formula, but you have no idea the importance of that f of a plus h minus f of a all over h formula yet. We will work with that a ton within chapter 2. So what is that telling us to do? Well, if I say evaluate f of a plus h minus f of a all over h, what is f of a plus h? What is that notation of just the singular f of a plus h? What is that telling me to do? A and h are inputs, not functions. F is the function.
To replace the x's with the a plus h.
Exactly. You know, if I said find f of 0, you guys would have no problem with saying, oh, you plug 0 in for x. So if I change that into, okay, if I want to find a plus h, f of a plus h, same rule applies. You're going to take a plus h and plug it in for x within the function. So that's going to be 2 times a plus h squared minus 5 times a plus h plus 1. That is f of a plus h. Right? But that's only a little part of my formula up here, right? Now I got to subtract f of a. Well, f of a is just plug it in a. Plug in a. Remember, I got to subtract that entire function. So f of a is going to be 2a squared minus 5a plus 1, all divided by h. So let's see what this evaluates to be. Okay, let's square a plus h. Just a little side work here. A plus h squared is a plus h, times a plus h. So foiling it out, that's a squared plus ah plus h squared. First outer inner last, right? Double up the middle. So second step down, this is 2 quantity, a squared plus 2ah plus h squared. Distribute in the negative 5. Negative 5a minus 5h plus 1. Distribute into negative to the whole right side here. Negative 2a squared plus 5a minus 1, still all divided by h. Okay, we got a little bit more distributive property to do, right? Let's do that before we simplify the top. So 2a squared plus 4ah plus 2h squared. Now let's minus 5a minus 5h plus 1 minus 2a squared plus 5a minus 1, all divided by h. I see some things here. I see a positive 2a squared and a negative 2a squared. So long, farewell. I see, can I do anything with the 4ah? Nah. What about the 2h squared? Nah. Ooh, negative 5a, positive 5a. Negative 5h? Yeah. Plus 1 minus 1? Goodbye. Okay, so what does that reduce into? That reduces into 4ah minus 5h. Oh, I forgot my plus 2h squared. I don't think order matters here. Plus 2h squared minus 5h, all divided by h. What next can I do? Cancel the h, right? I could essentially, just to show the intermediate step here, factor out an h from the entire numerator to leave a 4a plus 2h minus 5, all divided by h, and then we can see that, yes, it does indeed cancel. But remember, if every member of the numerator has a value in the denominator, you can cancel it out. So that means it's going to leave us with 4a plus 2h minus 5. And that is fully reduced. We can't do anything else with that. 4a plus 2h minus 5. Good. Got the same answers in my notes. It's always a good thing. Love it when I'm right. 4a plus 2h minus 5. You have no idea what that means right now, but oh man, that's a good one. We will do this a lot a little later on. That formula, that f of a plus h minus f of a all over h, is a pretty useful one. Okay, pretty useful. We'll use it a lot in chapter 2. The title of this lesson is 4 Ways to Represent a Function. Let's talk about those 4 ways. And representations of functions is really one of the key things that we'll talk about. We'll talk about representing functions verbally, like speaking them, like how do we talk about them. We'll talk about representing functions numerically, table of values. Representing functions visually by graph. And representing functions algebraically by formulas, by functions. Okay? Now, within calculus, what we're going to do is try to tie all of those together and really think about functions in a new way using all of these different types of representations to get a clear picture of what's happening within the function. Okay? If we can somehow describe it in words, that might inform how it looks numerically. If we can somehow describe what it looks like in a table, maybe that tells us something about what the graph is going to look like. Obviously, right? That's how we learned how to graph in the very beginning. Make a table, plot the points, look at it on the graph, connect your dots. If we can somehow see what it looks like on the graph, that might tell us something about how it's going to look algebraically. Obviously, right? If I was given a function, a quadratic, a U-shape, you automatically know what that equation looks like. Okay? What we're going to be doing is trying to amp up the difficulty in terms of, okay, what if the functions look really weird and wacky? What can we do then? Are there any different ways? Can I discuss it numerically to help me know what it's going to look like? If I see the graph, how can I tell what the function is going to look like? If I see the table, how do I determine what the graph looks like off of that? Okay. So again, it's going to be useful to go from one representation to another to give additional insight. Let's take a look here. Let's skip that page. Those of you who print out, I'm skipping that next page right there. When you turn on a hot water faucet, the temperature T of the water depends on how long the water has been running. Draw a rough graph of T temperature. Draw a rough graph of temperature as a function of time that has elapsed since the faucet was turned on. Go ahead and draw a graph of whatever you think this is going to look like. Okay. You turn on a hot water faucet. The temperature T of the water depends on how long the water has been running. Think about independent versus dependent variable in that case, and that will inform how you put it on your XY axis. The temperature T of the water depends on how long the water has been running. So it's temperature versus time graph. Draw a graph of temperature as a function of time. Go ahead, sketch one for yourself. Whatever you think it's going to look like. I gotta get used to the bells. What time is this bell ring? 32, that's right. Period 7 ends at 32. Got 16 minutes left. Perfect. I'm with you on that one. All right. Okay, what's on my x-axis? What's the label on my x-axis?
Time.
Time, right? It's time. How do I know that? I mean, I could think about it as independent versus dependent variable, but it also tells me right here, T as a function of time, temperature as a function of time, okay? temperature is my y value, my f of, right? And t is my x value, my input. So this is time. As time moves onward, what's going to happen to the temperature of the water? Right? Okay, you turn the faucet on. What's going to happen to the temperature? It's going to increase. Now, does the water automatically come out hot right away? No, it takes a while to get there, right? So I don't know what temperature we're starting at. It's probably not 0. So we'll just say it's somewhere up here. It's going to increase. And then at some point, is the water going to continually get hotter and hotter and hotter forever and ever and always? No. At some point, it's probably going to start leveling off, right? I mean, your water heater is only set to a certain amount of temperature, right? So it's probably going to, and it probably doesn't happen as like a distinct sharp point. It's probably going to level off at some point. Now, will it stay that hot forever and ever and always? No, what's going to happen eventually? The temperature is going to cool down. You use all the water up in your water heater, and it's eventually going to cool back down, back to room temperature, right? So generally speaking, that's what I think it might look like. And I guess if we wanted to keep going with this, it would stay consistent. If we kept on the water forever and ever, it would level off and it would stay that. And I guess maybe there might be some variation in terms of outside temperature having an effect on it. But that's the best we can tell right now. Okay. What did we do here? We took a representation verbally. We looked at a scenario and described it graphically. Wouldn't it really make sense to try to look at a table or an equation in this case? Because that's not really going to help us. But what we did here is used our verbal definition or verbal representation to figure out how it's going to look graphically. Take a look here. A rectangular storage container with an open top has a volume of 10 cubic meters. The length of its base is twice its width. The material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Express the cost of materials as a function of the width of the base. Okay. Now, I think we're given a verbal description of something here. Yeah. What we're going to do is draw a diagram to help us a little bit. But if I want to express the cost of materials as a function of the width, that's telling me to write a function, write an equation, right? That's telling me to write an equation. So I'm going to take this verbal description, verbal representation of a situation and turn it into a function, turn it into an algebraic equation here. So I am going to express cost as a function of the width. That's going to be my final answer, right? Cost as a function of width. Okay, let's first start off by drawing a diagram. I think that's going to help us here. We got a rectangular box, basically, right? With an open, I guess I can, it's solid there. With an open top. Rectangular storage container with an open top has a volume of 10 cubic meters. I know volume is equal to 10 cubic meters. I know volume is also length times width times height, right? Let's define width and height. The length of the base is twice its width. The length of the base is twice its width. So if I say this is wide, what is this? What is this? What's the length? If that's W, what's that? 2W. Okay. Are we told anything about height right now? Material for the base costs. Material for the sides costs. No, we're not. So we're going to have to get H out of here. We're going to have to figure out a way to get H out. Am I allowed to have two different variables within a function? Nah, you're playing with fire there. You don't want to do that. Let's just try to create a function just with W in it. Okay, well, think about this. If volume is length times width times height, that means my volume, 10, is equivalent to my length, 2W, times my width times my height. Okay, well, take a look at what I can do here. I can say that this is 10 is equivalent to 2W squared H. And when I solve that equation for H, meaning divide over the 2 and the W squared, that gets me 5 divided by W squared is equivalent to H. So I have just created for myself an equation that I can use in the end to get H out. I know H is equivalent to 5 divided by W squared. Okay, let's figure out what our cost is going to be here. I've done nothing with cost yet. All I did was work with the volume so far. Material for the base. Okay, material for the base costs $10 per square meter. I don't like that they use 10 again. That might mess me up here. So what is the area of the base? What is the area of the base?
Length times width.
Right.
3W. Or that is not right.
No, that's not right. 2W squared. There it is. I heard it. 2W squared is the area of the base. Capital B. Right? W times 2W. You did W plus 2W.
I don't know why.
I don't know. W times 2W is 2W squared. That's the area of the base, right? And it's $10 per square meter. So the cost of the base is equivalent to 10 times 2W squared, or 20W squared if we wanted to get that far. $10 times the area. Okay, but it's got a different cost for the material for the sides. Okay, well, what is it's $6 per square meter for the sides. So let's talk about cost for the sides. Let's talk about area of the sides first. Oh, that's not it. Come on. Area for the sides. All right, area for the sides. Let's go around. We got front and back. What's the area of the front and the back? What's the area of this front piece? WH, right? We have one of them? We got two. 2WH. Okay, and then we got the side, the right and left. I've got a 2W and an H. Okay, so the area for just this right side is 2W times H. 2WH. But do we have one of them? We got two. Right? That's just the area. Just the area. Right? This first piece here is just the front and the back. WH is our area. Double it front and back. Just the side, 2W times H, 2WH. Double it to get left and right. All right. Let's simplify this a little bit. So area of the sides is going to be equal to 2WH plus 4WH. All said and done. Area, capital area of the sides is 6WH. So what's the cost of the sides? Well, it's $6 times the amount of area, right? Just so happens these are both 6. So I say cost of the sides is equivalent to $6 times its area. Now, total cost is equivalent to its base plus the sides, right? Cost of the base plus cost of the sides. So I want to say total cost is equivalent to 10 times 2W squared plus 6 times 6W squared. Oh, sorry, WH. That's not W squared. WH. Okay, simplify that down a little bit. We got 20w squared plus 36wh. Okay, now, can I do this now? Cost as a function of width? I cannot, because there's h within my equation. Oh, wait. We had an equation for h. So let's take this and plug it right in there. Let's take that 5 over w squared and plug it right in for h. How's that going to help us? Well, now I've eliminated my h. Cost as a function of width is going to be 20w squared plus 36w times 5 over w squared. And now all we need to do is some simplification. Because that's equivalent to 20w squared plus, what's 36 times 5? 180? Is that right?
Yep.
180. And then I got w over w squared. So just leaving me with over w. And there it is. Cost as a function of width is right there. I could also represent that as 180 w to the negative first, right, if I really wanted to. You're going to find that leaving things with negative exponents is kind of like okay now. We're going to get into things where, we're going to get so far into it. Rationalizing the denominator is going to go away a little bit. You're not going to have to rationalize the denominator as much anymore. I know. And like leaving things over w, it's actually better to write it as a negative exponent in terms of what we'll do for calculus here. All right, looks like we only got a couple more slides left to finish up tomorrow. And yeah, sound good? Day 1 in the books.